Okay, all right, we're going to continue our discussion of red-black trees today. In our last lecture, we saw the principal operations that are done on red-black trees or dictionaries, and today we want to look at how to perform two additional operations, namely joining two red-black trees into one and splitting a red-black tree. Okay, all right, these two operations find application in several places. One that I could mention right now is in data structures for dynamic packet routing tables in the internet. So one of the first log-n structures proposed out there to handle packet forwarding and insertion and deletion of new and old rules involved red-black trees, and there was extensive use of joins and splits. Okay. But there's certainly many other applications, and we'll mention another one when we take a look at B trees later. Okay. All right, so the objective is to end up with algorithms to split and join red-black trees in logarithmic time. And for that purpose, we will need to introduce a new term on red-black trees. Okay. So the new term is rank. So with each node in a red-black tree, I will associate a rank. So the rank of the node X is the number of black pointers on the path from X to an external node. And if you recall the correlation between pointer colors and node colors, you'll see that this is really the same as the number of black nodes from X to an external node. But in this count, we don't count the node X, whether it's black or red. Okay, so the number of black nodes excluding X from X to an external node, that's the same as number of black pointers. Okay, if you're sitting at an external node, okay, then the number of black pointers needed to go from an external node to an external node is 0. Similarly, the number of black nodes on the path from this external node, the external node itself is colored X, is colored black, but we can't include that node in the count. Okay, so there are no black nodes other than itself on the path from an external node. Okay. All right, so let's look at an example out here. Okay, so here's a red-black tree. Okay, all of the external nodes have a rank that is 0. Now, if I look at this node here, the number of black pointers on a path from here to an external node, it doesn't matter which external node you go to, the number of black pointers is always the same, given the definition that we had last time for a red-black tree. Okay. So there's one black pointer, so its rank is 1. Same thing here, there's one black pointer. If you come out here, number of black pointers from here to an external node is 1. Regardless of which of these 4 external nodes you go to. Also, the number of black nodes on the path from here to an external node, excluding itself, okay, you go through a red node and a black node, so it's only 1. Okay. All right, the rank out there is 1. Okay. Number of black pointers is 1. If you come over there, the rank of this node is 1. Okay. Rank of that node is 1. There are 3 black pointers in its 3 external nodes in the subtree. Regardless of which one you go to, you go through exactly 1 black pointer. Okay. Here there are 2 external nodes in the subtree. You go through 1 black pointer. Over here, 2 external nodes in the subtree. You go through 1 black pointer. Okay. From here, okay, you got 1, 2, 3, 4, 5 external nodes. Independent of which one you go to, you'll have to go through 2 black pointers to get to it. Okay. Equivalently, you have to go through 2 black nodes, okay, excluding the origin. Okay. All right, rank of this node is 2. Number of black pointers is 2 to an external node. Over there, the rank is 2. And then for the root, the rank is 3. All right, so the rank of a node is the number of black pointers from that node to any external node in its subtree. That's the same as the number of black pointers, provided you exclude the node you start at in the count. Okay. Same as number of black nodes, provided you exclude the node you start at. All right, any questions about rank? Okay. All right, so all right, the rank is 0 for an external node. Okay. If you look at the parent of an external node, okay, its rank will be 1 because the pointer that goes into an external node is black. If you look at a node X and if it has a parent, okay, then the rank of X will be less than equal to the rank of its parent. Okay. So as you go up the tree, ranks go up. Okay. But when you go from a node to its parent, the rank may go up by at most 1. Okay. So the rank of the parent is at least as big as the rank of the child, and isn't more than 1 more than the rank of the child. If you have a grandparent, okay, when you go from a node to the grandparent, the rank has to change. Okay. If the rank doesn't change, then you must have 2 red pointers in a sequence, or 2 red nodes in a sequence. Okay. So since when you go from a node to the grandparent, you have to go through at least 1 black pointer, maybe 2, the rank has to increase, either by 1 or by 2. Okay. Now you can prove that any binary tree to which you can assign ranks to satisfy the properties that I just listed is a red-black tree. So if you forget about colors, if you can assign integer ranks to the nodes so that the rank of an external node is 0, the rank of the parent of an external node is 1, as you go up, ranks increase. When you go from a node to its grandparent, the rank has to go up. When you go from a node to a parent, the rank may or may not go up, but may go up by at most 1. Okay. So if you satisfy those properties, then you have to have a red-black tree. Okay. And actually, once you have placed ranks on nodes according to those properties, you can figure out the color of each node. Okay. So if the rank doesn't change, that pointer has to be red. If the rank changes, that pointer is black. Okay. All right. So if you look at a pointer from a parent to a child, okay, it's a red pointer if the rank doesn't change. It's a black pointer if the rank changes, and if the rank changes, it can only change by 1. Okay. And then if you know the color of the edges, you can figure out the color of the nodes. For the root, you have this constraint, the root is always black. All right, so using ranks is equivalent to using colors. Okay. Now, if you know the rank of the root of the tree, and you know the color of the nodes, the color of the edges, then starting from the root as you go down, you can compute the rank of every node. Okay. So you don't really have to store the rank of every node. You just store the rank of the tree altogether and then store the colors. And then as you go down, you can compute everybody's rank if you have an algorithm that requires knowledge of rank. Okay. And that's really what we'll do. We'll store ranks with the root, and then colors on the nodes or colors on the edges. Okay. All right, using the rank definition, one can prove the same bounds we had the last time, that the height of a red-black tree lies between log n plus 1 and 2 times log n plus 1. Okay. We know that the height is going to be at most 2 times the rank. Okay. Because every time you go, say, downwards or you go upwards, it's only when you go to from a node to its parent, the rank may not change, but once you get to the grandparent, the rank has to change. Okay. So the worst that can happen to you is that the height is 2 times the rank. Okay. Of course, the height can also be equal to the rank, so it's somewhere between rank and 2 times rank. Now, since the rank gives you the number of black pointers, okay, it tells you that you can't really have an external node at the first so many levels. If you had an external node at, say, level 2, okay, then you only need 1 black pointer to get to that external node. Okay. If you had an external node at level 3, you only need 2 black pointers to get there. If you had an external node at level 6, you only need 6 black pointers. But since the rank is the number of black pointers needed from the root to the external node, and all of them are equidistant, you can't have an external node at levels 1, 2, up to rank of root. Okay. You can have an external node 1 level after that. Okay. So those levels are populated by internal nodes. So if you count only the number of nodes on those levels, you get a lower bound on the number of nodes. Okay. So we count only the nodes on those levels. That works out to 2 raised to rank minus 1. Okay. So the number of internal nodes is at least 2 raised to rank minus 1. Alternatively, the rank is no more than log of n plus 1, n being the number of internal nodes. Okay. And then coupling this with this thing here, you get that the height is at most 2 times log of n plus 1. Okay. So you get an alternative proof that the height of a red-black tree is at most 2 times log of the number of internal nodes. Okay. All right, any questions about that proof? All right, so one can derive the properties of red-black trees without resorting to colors by simply having ranks associated with every node, and you can do everything based on ranks, and you can infer the colors from the ranks. Okay. Now, it's cheaper to store colors than ranks. Because colors, you only got red and black, so you need 2 bits. If you're trying to store the colors of pointers, so left pointer can be stored, color can be stored with 1 bit, 0 being red, 1 being black. And similarly, the right child pointer color can be stored with 1 bit. Or if you're storing node colors, you only need 1 bit to store the color of that node. But ranks can range up to log of n, so you need more bits to store ranks with nodes. So it's cheaper to store colors than ranks, but we just store the rank of the root instead of ranks of all of the nodes. All right, so let's take a look at the 2 operations that were of interest today. One is join, the other is split. The joins are really constrained in terms of the input that is permissible to the join. Okay. So the join operation takes 3 inputs, S, M, and B. Okay. S is a dictionary where the keys are what we'll call small keys. Okay. B is a dictionary that has large keys, and what small and large mean is really with relationship to this additional pair that's going to be in the resultant dictionary M. Okay. So all of the keys in S are smaller than the key of M. Okay. All of the keys in B are bigger than the key in M. Okay, so that's what we mean by small and big. Okay. So it's not that you have 2 arbitrary dictionaries that are being joined. All of the keys in one dictionary S are smaller than all of the keys in the other dictionary B. Okay. All right, so this would be a 3-way join. We're given 3 things, but you could do a 2-way join where you're not given an M. Okay, and that's similar to a 3-way join. All right, the result of the join is a single dictionary that contains everybody in S, everybody in B, and the additional pair M. The join is a destructive operation, and that after you have done the join, S and B do not exist as independent dictionaries. Okay, so you can alter them any way you like while you're creating your new dictionary. Okay. All right, so let's first take a look at how you could do a join if you didn't really care about red-black trees. If all you had were binary search trees and you said, well, do a three-way join on binary search trees, not necessarily red-black. Okay. Well, in that case, the join is pretty simple. You just get a new node, stick the new pair into it, make S the left subtree of that new node, and B the right subtree of that new node, and you get a new binary search tree that contains both the dictionaries as well as the pair M. Okay. So a join in an unbalanced binary search tree is a simple operation, takes order one time. All right, this of course will not work if you're dealing with red-black trees, because maybe down here the number of black pointers on paths to an external node of 4, and maybe here it's 40. So once you do this, even if you make this a black node and a black pointer, okay, so the root will be black. If you've got a black pointer here, well then you have 5 pointers on root to external node paths there and 41 out here, which doesn't satisfy the red-black property. Okay. So this simple thing doesn't work for red-black tree joining. Okay. All right, so when you're joining red-black trees, the join splits into 3 different cases depending upon the relationship between the rank of the small tree and the big tree. Okay. When the ranks of the 2 trees are the same, then of course the simple thing works. Okay. So for example, if the rank here had been 4 and there it was 4, well then if I create a new node M, the number of black pointers from here to an external node going this way will be 5, and it'll be 5 that way too, so the rank of that node is 5 and you're okay. So when the rank of S and B are the same, it's order 1. You do the same thing that you would have done for unbalanced binary search trees. Second case is when the rank of the small tree is more than that of the big tree. Okay. So in that case, what we'll do is we'll start at the root of the small tree and make right child moves until I reach a node whose rank is the same as that of the rank of the big tree. Okay. We know that as we go downwards, at worst, every 2 moves you make, the rank will drop by 1. Okay. You never see big drops in rank, so if you go from a node to its child, the rank may be the same, or it may go down by 1, but it's not going to go down by 6 or 10 or something. Okay. So if you start with somebody here whose rank is 40, at some point you'll reach someone, well, after at most 2 moves, you'll reach somebody whose rank is 39, and then after at most 2 moves, somebody whose rank is 38, 37, 36, 35, and so on. Okay. So we make right child moves until you reach the first node, X, whose rank is the same as that of B. And we're guaranteed that we're going to reach such a node. Okay. The pointer into this node will have to be black. Okay. Because if the rank of B is, let's say, 10 and the rank out here is 15, well then this node's rank is 10, that's where you stop, which means this node's rank must have been 11. Okay. If this node's rank was 10, we'd stop out here. Okay. We're going to stop at the first node whose rank is 10. So if this node's rank is 10, this node's rank has to be 11. So you've got to have a black pointer here because you got one more black pointer from here to an external node than from there. Okay. So you X has to be a black node. Okay. All right, so we stop at the first node whose rank equals that of B. That has to be a black node. Call that node X. Okay. That node is going to have a parent. Okay. It can't be the root. If it was the root, then we would be in the previous case. Okay. So this node has a parent, call that px. The color of the parent is not known. Okay. The color of the parent could be red, it could be a red node, it could be a black node. Okay. So that's why we've got this broken pointer here, indicating that we don't know the color of that pointer, and I don't know the color of that node. Okay. The time required to move from here to there. Okay. The number of moves you make is at most 2 times the rank difference. Okay. For every 2 moves, the rank has to drop by at least 1. Okay. So if the rank difference is 5, after 10 moves, you got to reach x. Okay. So it takes you time, which is 2 times the rank difference at most, to get here. Once we get here, I will then do my construction into this point. Okay. I will insert that middle pair as well as the big tree. Okay. I'll create this configuration here. So I'll get a new node into which I stick the middle pair. Down here I've got this entire subtree. Okay. So this entire subtree becomes the left subtree of M, and the big tree becomes the right subtree of M. Okay. All right, so the first thing to note with that construction is that you have a properly configured binary search tree. Okay. M is bigger than the key there. In fact, M is bigger than everything in the whole tree. Okay. So M is bigger than that fellow. Everybody down here is smaller than M. In fact, everybody in that whole tree is smaller than M. Everybody down here is bigger than M. Okay. All right, so you've got a properly structured binary search tree. Of course, it may not be red-black. Okay. All right, so first we verify that we've got a binary search tree. Okay. This node comes in as a red node. As a result of that, the number of black pointers on paths from the root to external nodes is not changed. Okay. So previously, to get to the external nodes in A and B, okay, down here, okay, we came to Px, we followed a black pointer, got to X. Okay. Now you come to Px, you follow a red pointer and then a black to get to X. Okay, so it's the same as before. And then to get to the external nodes here, okay, the number of black pointers is the same as on this side, because the rank of X is the same as rank of B. Okay. So all root to external node paths have the same number of black nodes, same number of black pointers. Okay. The problem that we may have is we don't know the color of this fellow. Okay. If this fellow is black, you're okay. If this fellow is red, you have 2 red pointers in a sequence, and so you violate the red-black property. Okay. All right, so if it's a black node, you're finished. If it's a red node, you have 2 consecutive red nodes or 2 consecutive red pointers, and we need to rectify that. And we saw how to rectify that when we did an insert. Okay. So when you have 2 of these fellows, you have, that's P, Px, Gp, you classify the type, you either do a color flip or a rotation. And okay, color flips require you to move up 2 levels, a rotation terminates. Okay. So we perform exactly the same tasks that were being performed during an insert to fix the 2 red pointer in a sequence problem. Okay, going back up the tree. And the time required, okay, since the distance you move down is 2 times the rank difference at most, the distance you got to move back up is the same at most. Okay, and it takes you only 1 unit of time for every 2 levels you move up. Okay, so the total time to do the join is linear in the rank difference. And that difference can at most be log of the total number of elements. Okay. So you can do the join in logarithmic time. Okay. All right, any questions about how a join works? All right, so let's turn our attention, well, I guess we have one other case. This works the same as the other case. Okay. So if the rank of the small tree is less than that of the big tree, well then on the big tree you start by making left child moves until you reach the first node x whose rank equals that of s. And then you perform the same operation out there. All right, so let's turn to split. Okay. So the split operation, you're given a key, and then based on that, you need to split the tree into 3 parts. Okay, so it's kind of the inverse of the join. Okay. So we'll split the tree into a dictionary of pairs whose key is smaller than the split key, a dictionary of pairs with key bigger than the split key, and then the middle pair whose key equals the split key. Of course, the dictionary may not contain a pair with this key, in which case M would be null. Okay. All right, any questions about what we want to do? Okay. We just want to reverse what took place in a join, though one exception is that the split key may not have a corresponding pair. Okay. All right, first let's see how we would do a split in an unbalanced binary search tree. All right, suppose this is an unbalanced binary search tree. And these lowercase letters represent subtrees, and the caps represent pairs. Okay. Right, so I'm going to do a split, and the split key corresponds to the key in this node. Okay. So to do the split, I'm going to traverse a path from here. My split key is bigger than this, I'll come here. Split key is smaller than this, I come here. It's bigger than this, smaller than that, bigger than E, I come here and I find a match. Now what I'll do is on the way down, while I'm trying to find the location of the split key, and if the split key is not there, I'll fall off the tree somewhere. Okay, so I'll follow a path dictated by the split key. On the way down, I will partition the tree into the small and big trees. Okay, so for that purpose, I'll start with 2 header nodes, one for the small tree and one for the big tree. Okay. All right, so when you come from here to here, we know that the split key is bigger than this key, and so it's bigger than everybody down here. Okay. So A and this subtree little a belong in the small tree. So I will set up a pointer here to this node. Okay. Conceptually, that's what I'm doing. Okay. So I set up a pointer in the header node, make the right child of the pointer A, and then this whole thing comes for free. All right, so now I'm at this node. Okay. I compare my split key with the key out here. My split key is bigger than, my split key is smaller than that. That's why I'm going to come this way. So this guy is bigger than the split key, and everybody here is bigger than the split key. So this whole thing belongs in the big tree. And to effect that, I'll make the left child of the header node this node here. Okay. So effectively, I'm doing this. All right, then I'm here. My split key is bigger than C, so I'm come here. So C is smaller than the split key, and everybody here is smaller. So this whole thing belongs in the small tree. Okay, but everything here is also bigger than A because of the path that I took. So this whole stuff can be made the right subtree of A. So I change the right child pointer here. Okay, so I do that. All right, now I'm here. And I'm going to move this side. So my split key is smaller than D. So D belongs in the big tree together with this right subtree. Okay. But the stuff in here is smaller than B because of the path that I took. This is in the left subtree of B. So I'll attach this now as the left child of B. So I keep track of the last node that was attached, and if I find anything else, it'll become the right child here. If I find anything in this tree, it'll become the left child over there. Okay. All right, so now I look at this guy. My split key is bigger than that, so this belongs in the small tree. So E becomes the right child of C. Okay. Right, then I reach this node. I get a match. So its left subtree is smaller, so its left subtree belongs in the small tree. Its right subtree is bigger, its right subtree gets attached into the big tree. Okay. And then I throw away the two header nodes, and I've got my small tree, my big tree, and the element. Okay. Right, so if we didn't care about balance, we could split a binary search tree in time proportional to the height of that search tree. You just follow a path dictated by the split key and move subtrees into S and B as you go down. If you did this on a red-black tree, you may not end up with a red-black tree. You can check that out on your own, because the subtrees that you're attaching don't preserve the rank property. All right, so something you can verify at home is that this strategy doesn't work for red-black trees. We need a different strategy, and the strategy that we're going to adopt is really going to be a two-pass strategy. In the first pass, we'll trace the path to the node that has the split key, if such a node exists, without partitioning the tree. On the second pass, we will back up the tree, going back to the root, and at that time we will split the tree. Okay. When we split the tree, we will need to attach parts of trees to a currently built small tree or big tree. In the case of unbalanced search trees, we did that simply by changing one child pointer. Here, the attachment is really going to be done by the use of the join operator that we just looked at. So the join will ensure that you can take two red-black trees of any rank and create a new red-black tree. Okay, so let's look at the example. All right, so in the first pass, I'm going to start from here, travel down, and come there. I'm not going to split the tree. Okay. All right, so once I have reached this fellow, the left subtree is known to be a red-black tree, and the right subtree is known to be a red-black tree. These will be my initial small and big trees. Okay. So small begins with F and that with G, and so it's known to be a red-black tree, and every time I add things to S and B, I'll ensure that the result is a red-black tree, and so when I finish, S and B will be guaranteed to be red-black trees. Now at times, the key that you're searching for will not be present, so you'll fall off somewhere. Okay. So at that time, you can start with an empty S and an empty B, and then retrace your path back up the tree. Okay. So if M is present, then we'll start with F and G like that, or S and B like that. If M is not present, we fall off here, then we can start with an empty S and an empty B, and then go back up. All right, so I retrace the path, I come to the node E. Okay. I've come here from the right subtree, so I know that E is smaller than the split key, and everybody here is smaller than the split key, so this stuff belongs in the small tree. Okay. So I'm going to do a three-way join of this stuff with the small tree. Okay. Now, So there's no way to go back from here. Let's go back from here. Okay, so if you look at the setup, we're coming from the right subtree. Okay, so when you're coming from the right subtree, everything that you have seen so far, okay, is going to be bigger than this guy. Okay, doesn't matter where it got placed. Everything you've seen so far, because we're starting from the bottom, is going to be bigger than this guy. Okay, so when you do the three-way join, we've got E. Everybody here is smaller than this middle key, and everybody in S is bigger than that. So that's a valid configuration for our three-way join. Okay, so when we're here, okay, we're going to do a join of this fellow. Everybody here is less than this middle key, and everybody in S so far is bigger than that. Okay, so that's a valid join. I run my join operation and construct a new S. All right, so now I'm finished with everything that was down here. I'm going to back up here. Since I'm coming from the left, okay, since I'm coming from the left, the split key is smaller than D. So D and everybody here belongs in the big tree. Since I'm coming from the left, everybody I've seen here, okay, is smaller than that guy. In particular, everybody you accumulated in B so far is smaller than this guy. Okay. So when I do the join with B, I know that the current B has things smaller than D, and so I can use my three-way join, okay, which is small items, a middle item, big items. All right, so then from here I'm going to come out here. You're coming from the right subtree, so everything you've seen so far is bigger than that. Okay. Also, the split key is bigger than that. So this fellow belongs in the small tree, so does that belong in the small tree. I do a join with the small tree. Okay. Everybody so far in S is bigger than big C. So the join that we looked at a little while ago works. Okay. All right, then we're going to back up to B, and you're coming from the left. So everybody you've seen so far is smaller than that guy. The split key is smaller. Okay. So B and its right subtree go into the big tree. Okay. So we'll do a join. Okay. So these items are known to be smaller than the item in B, and everybody in little b is bigger than the item in that root node. Okay. All right, then we're going to back up over there to do a join. Okay. So again, you're coming from the right subtree. So this guy belongs in the small tree. So does that guy belong in the small tree? Everything you've currently put into the small tree is bigger than this guy. Okay. All right, so when you're done, your small and big trees are guaranteed to be red-black trees. Okay. All right, questions about how that split works? Okay. So it's a two-pass split. Top to bottom is used to locate the split element, and then bottom to top to actually create the split, the small and big trees. All right, if you analyze the complexity of this, there are a large number of joins taking place. In fact, there could be log n joins taking place, because you're starting, the height of this thing could be up to 2 log n, so you're starting somewhere down here, and each time you move back up one level, you do a join. So potentially you could be doing 2 log n joins. one could say that a join takes log n time. You do 2 log n of those, so that's log square n. Okay. But if you do a more careful analysis, which says the complexity of a join is the difference in the ranks of the 2 trees that you're joining. Okay. And then what happens is if you take the rank difference here plus the rank difference there plus the rank difference here, and similarly do those ones separately for their rank differences, you'll find that most of the ranks cancel out, and the only thing that remains is the rank of the final result and the rank where you started. And that rank difference is logarithmic. Okay. So if you work with the complexity as rank difference, then you add up the complexities of the different things, and you'll see that you end up with something like a telescoping sum, and the only thing that remains is the final rank and the initial rank, and that difference is at most log n. Okay. So the complexity of the split is actually log n, and we're not going to go through the analysis here, but you can read it from the book. They've done the analysis over there. Okay. All right, any questions? Okay, so we'll stop here.